Now that we've explored both electric and magnetic fields and have learned a lot of different right-hand rules, I'm going to take a moment to review the concepts in each right-hand rule. So first of all, let's look at stationary charges. So if I have a stationary charge Q1, we know that creates an electric field E1. Now, Q1 doesn't experience a force due to its own electric field. Remember, every force is due to an interacting pair, so you can't exert a force on yourself. However, if I place a second charge, let's say Q2, in this external electric field E1, this Q2 experiences a force because E1 is external to it. Okay, and of course, if Q2 were negative, then the force it would experience would be going in the opposite direction of the field. Okay, so again, you don't feel your own field, you only experience forces due to fields that are external to you. If I have a charge and it's moving, then it creates both an electric field and a magnetic field. Okay, so the electric field looks like just like it did before, okay? This has electric field lines radiating outward. But the magnetic field that it creates, you find the direction of that using the right-hand rule. And the right-hand rule we use for this situation, okay, so this is magnetic fields created by moving charges. I'm going to say you do the curly right-hand rule. So what that means is you put your thumb in the direction of the velocity and your fingers curl in the direction of the magnetic field lines. So you can see here, if your thumb is moving to the right, your fingers curl coming out of the page on top and going into the page on the bottom. So they're actually making loops like this, but we simplify the loops by just drawing dots, which means out of the page, and X's, which means into the page. Now, if instead of a charge moving to the right, if we had a current moving to the right, that's basically the same thing, right? Conventional current is the flow of positive charges. So again, all you have to do is put your thumb in the direction of current and your fingers curl in the direction of the field. So again, it comes out of the page on top and into the page on the bottom. Okay, and of course these are actual loops, but I'm drawing the dots and X's just to make the graphs be a little bit more clean. This magnetic field for a long current carrying wire is mu naught I over 2 pi r. So this describes, okay, the magnetic field created by this current carrying wire. And you can find magnetic fields created by moving charges using either Ampere's law or the Biot-Savart law. Okay, so now we're going to look at what happens when you put a charge in an external magnetic field. So here we saw that if you put a charge in an external electric field, it would experience a force. And similarly, if the conditions are right, if you put a charge in an external magnetic field, it will also feel a force. But there's one trick. Okay, so we know that the force due to an electric field is just Q times E. So basically, as long as a charge is in an external electric field, it'll experience a force. There's nothing too tricky about that. However, with magnetic fields, the equation is actually QV cross B will give you the magnetic force that this charge experiences. So because this is a cross product, it actually depends on the angle between V and B. So we can rewrite this as Q times the magnitude of the velocity times the magnitude of the magnetic field times the sine of the sandwich angle. Okay, this is the angle between V and B. All right, so let's take a look at a couple examples. Let's say that you have a magnetic field going to the right. If I place a charge in there and that charge is at rest, well, then the magnetic force is QVB, sine of the sandwich angle. Well, in this case, velocity is 0, so that means there is no magnetic force acting on that charged particle. Okay, that's different than the electric field case, right? In the electric field, it doesn't matter if that charge is moving or not, it would experience a force. Here, it doesn't experience a force unless the charge is moving, and the charge has to have some motion that's perpendicular to the B field. So we'll see that next. So here, let's say that now we have the charge moving, but it's moving aligning with the magnetic field. So in this case, we see V is parallel to B. All right, so now we do FB is QVB times the sine of the sandwich angle. Here, the angle between velocity and the magnetic field is 0, and the sine of 0 is 0. So this also results in no magnetic force. So the only way you can get a magnetic force is if you have some component of this velocity going perpendicular to B. So in this case, they're perfectly perpendicular. So now if I do the equation, QVB times the sine of the sandwich angle between V and B is 90 degrees. So sine of 90 is 1. And we see that the magnetic force is maximized when this angle is 90 degrees. Now, if you had something that wasn't quite 90, like let's say you had some angle alpha, in this case, you would also get a magnetic force, right? FB would be QVB sine alpha, but it wouldn't be as large as this scenario. Okay, and you can see that it does still have some component of the velocity going perpendicular to the B field, which is why we get some force, but why that force isn't as large as it would be in this scenario. Okay, so that's how we find the magnitude of the force, but we also need to figure out what direction the force is in. Okay, so for the first example, we'll do the same one that we just had, where the B field is going to the right, and this positive charge is moving to the top of the page. Okay, now for us to look at this particular situation, we're going to do a slightly different right-hand rule. So I like to save the curly right-hand rule for these magnetic fields that are created by moving charges. And for the forces, I like to do a different right-hand rule. For the forces, you want to put your first finger in the direction of the velocity, your second finger in the direction of the magnetic field, okay? And your thumb will then point in the direction of the magnetic force. Now you want these to be perpendicular, but you want to be pointing with your first finger. You don't want to be pointing with your second finger. So if you're giving someone the bird, okay, you're doing it wrong. You want to make sure your first finger is pointed, your second finger is perpendicular to that, and your thumb is perpendicular to both of them. So for this example, the velocity is going to the top of the page, so that's my first finger. The magnetic field B is going to the right, so I turn my hand, and then I get a force going into the page. So in this particular case, the force is actually going into the page. Okay, and you'll always notice the force is perpendicular to both V and B. All right, so what if I had a situation like this, where now I have maybe a magnetic field going into the page, okay? And let's say I had a charge moving to the right. Okay, so again, you have your first finger in the direction of the charge, your second finger in the direction of the field. So in this case, the field is going into the page, and you can see that my thumb is pointing towards the top of the page. So in this case, the magnetic force is towards the top of the page. Okay. If I had a negative charge, So you have the same field, but now I have a negative charge that's moving in this direction. I have two options. I can either just reverse the answer that I got with the right-hand rule, so I know that the actual force is going to be going to the bottom of the page, or you can use your left hand. So here you could say the charge is going to the right, the magnetic field is going into the page, and then my left hand gets a force going downwards. Okay, and finally, of course, if you were having a current, so let's say that you have a magnetic field coming out of the page here. Okay, you had a current going to the right. Again, currents are the same thing as moving positive charges. So your first finger is the direction of the current flow. Same thing, so now your middle finger is still the B field, your thumb is still the magnetic force. So here you have current, the magnetic field is coming out of the page, and so you get a magnetic force going down the bottom of the page. Now this equation is actually IL cross B. So it's really similar to QV cross B. It's just I and L take the place of the charge times the velocity. This is just the current times the length, and they're actually equivalent. So L would just be the length of that wire. Okay, so now we're going to kind of combine both of those stories, okay? So we have the situation where a charge creates a magnetic field, and we also have a situation where a charge that's in an external magnetic field experiences a force. Okay, so again, this is the magnetic field created by I. These magnetic fields are external. They're created by something else, and then when you put a charge in them, they feel a force. So let's say that now, let's do a situation where we have a current I going to the right, and we have some positive charge that's moving to the top of the page. Okay, I want us to find the magnetic force on charge Q. Okay, so let's call this charge Q. Okay, so Q creates a magnetic field, right? We said that Q is creating a magnetic field. It's circling around that charge. And I is also creating a magnetic field. Okay, so again, we can do our curly right-hand rule to find the magnetic field created by I. The thing is, you only feel the magnetic field that's external to you. So if I want to know what the magnetic force is on this charge, I don't care about the magnetic field it creates. I care about the magnetic field that everything else creates. So what I'm going to do is I'm going to say that this current I, okay, it creates a magnetic field, and I use the right-hand rule. It's coming out of the page above it and into the page below it. So this charge, because it's above it, it knows the magnetic field is coming out of the page. It doesn't care about what's happening down here. It cares about the magnetic field that it's in. So now we can say, all right, now we have a charge. Okay, positive charge V, and a magnetic field coming out of the page, and we want to find the force on it. So it's just V cross B, and the force would be to the right. So these problems look a little bit confusing, but you just have to make sure that you figure out which field is external to the charge that you're concerned with, and that's the one that exerts a force. So that's the basics of the magnetic force situation. Now we're going to look at what happens when we talk about Lenz's law and Faraday's law. Okay, so for Lenz's and Faraday's law, what matters is this idea of a changing magnetic flux. Okay, so let's say that you have a loop of wire, and it's not connected to a battery, it's not in any magnetic field, it's just sitting there. Nothing's going to happen, right? If you have no voltage, then no current will be flowing. Okay? Similarly, if you put it in a magnetic field, and this is a constant magnetic field that's not changing, nothing will happen. The only time you get something to happen is when the magnetic flux, okay, or you can think about it as the number of field lines through this loop starts to change. So if you do have a changing magnetic flux, this loop will create an EMF that will cause a current, and that current direction will basically be producing a magnetic field that will counteract the change. Okay, so what does that mean? Let's just do an example where the magnetic field external is here in black. So the external magnetic field is going into the page. Now, I will just tell you that right now, let's have it such that the magnetic flux is increasing. Okay, so maybe the field's getting stronger, or you could have the area getting bigger or something like that, but probably just the field's getting stronger. So here, the B is external and into the page, and the magnetic flux is increasing, so it's getting bigger and bigger. This loop is going to create a current that will create a magnetic field that will counteract the change. So here, since the external magnetic field is into the page and it's getting bigger, the induced magnetic field is going to counteract that. So if you're getting more and more field into the page, the induced magnetic field is going to go out of the page to cancel out that change. Okay, so if the induced magnetic field will be this red thing, it'll be coming out of the page. And so that means if you have your right-hand rule, okay, you're talking about the curly right-hand rule, the current that would have created that out of the page is going counterclockwise around this loop. Okay, so you can see that if you take your thumb and go around the loop, in the center of the loop, your fingers are coming out of the page. All right, so now let's do an example where it's the same setup. Okay, so B external is still into the page, but now let's say the flux is decreasing. Okay, so now what you have is you have this flux that's going into the page, but you're getting less and less of it. And so the B induced wants to get it back to what it was. So because you're getting less and less, the B induced wants to put more into the page. So this red is the B induced. And this B induced is created by a current. So again, if you know that the B induced is going into the page, then your current has to be going around clockwise. Okay, because you do the curly right-hand rule to get the current going clockwise. Okay, so just for completeness sake, let me try a couple more. So let's say now that you have an external B field coming out of the page. Okay, if the flux is increasing, so again, if you're getting more and more flux out of the page, then the idea is that the induced B field wants to cancel that, right? If it's getting more and more out, the induced B field wants to go in. So the B induced would be into the page. Okay, and again, if you do your right-hand rule, if you have into the page on the inside of the loop, then your current has to be going around clockwise. Okay, this one is also clockwise. All right, but as a final example, Okay, here if you have the B external is going, sorry, this is out of the page. Okay, if you have the B external coming out of the page, and now let's have the flux decreasing. Okay, so you have B field coming out of the page, but it's getting less and less and less. Then the B induced will want to also come out of the page to try to get it back up to normal. So that's your B induced in the red. And so that means that your current that would have created that B induced has to be going counterclockwise. Okay, so the final part of Faraday's law is that even if there weren't a loop of wire, the changing magnetic field can still create an electric field. And the electric field direction would be the same direction as what you would have gotten if you just did that processing and found the direction of the current. So let me show you what that means. So here, let's say, okay, that you have, actually, I'll go ahead and say you have a circle of magnetic field here. Okay, so this is a magnetic field that's coming out of the page. Okay, so this is just a region of magnetic field. There's no wires or anything right here. Still, if the flux is increasing, nature will want to create a magnetic field to combat this increasing flux. So if it's out of the page and increasing, then the B induced must be into the page. So you get these X's, right? So if this were a current, you know, X's are into the page, so the current would be going around this way. But even if there's not a wire, what you'll get is you'll get electric fields going in that direction. So another example would be, let's say you had same setup. Okay, so again, the B field is out of the page. Except this time the flux is decreasing, so it's getting weaker. Okay, let's say the field's getting weaker. So in that case, if it's coming out of the page and it's getting less and less, then the B induced wants to go out of the page to try to bring it back to what it originally was. So you get dots for the B induced. And so again, if you do the right-hand rule, that would have been a current going around this way. But instead of a current, you're actually getting E fields. So the way you would solve those electric fields is using this approach of Faraday's law, which is a little bit different. In these cases, if we just want to know the currents, then we know the EMF induced is minus the change in magnetic flux over time, and then EMF induced is just I times R, right? Just like if you were talking about Ohm's law. So when you're talking about currents, you can think about as this thing happening because it's creating an EMF. But if there's no wire there, you can still consider Faraday's law, but it's creating an electric field instead.